Welcome, everyone, to today's Explainer. I am absolutely thrilled to guide you through this because, honestly, we're looking at one of the most fascinating transformations in all of chemistry. We are going to explore how substituting just a single atom, the oxygen atom, fundamentally alters the entire behavior, purpose, and physical nature of a hydrocarbon chain. Let's get right into it. Think about your basic hydrocarbons kind of like a factory standard base model car. It gets you from point A to point B, sure, but it's pretty unreactive and plain. Now, adding an oxygen atom to that basic hydrocarbon, that is exactly like slapping on massive off-road tires, a supercharged engine, or a luxury interior. That single modification completely transforms those unreactive molecules into totally new machines. Suddenly, we get vital medicines, the sweet fragrances of fruits, the foundational structures of fats and oils, and even heavy-duty industrial solvents. This abstract chemistry isn't just theory. It is literally the direct blueprint for our real world. Okay, let's dive into this. Here's our agenda for today. We'll start with oxygenated hydrocarbons, look at alcohols and hydroxyls, learn about classifying alcohols, cross the ether's oxygen bridge, explore aldehydes and ketones, and finish up with physical properties. Section 1. Meet the oxygenated hydrocarbons. The oxygen advantage. When oxygen enters the chat, it doesn't just create one type of molecule. It spawns an entire grand family. This expansive family includes alcohols, ethers, aldehydes, ketones, carboxylic acids, and esters. The secret sauce behind these distinct personalities is something called a functional group. A functional group is basically just an atom, or a specific group of atoms, responsible for imparting specific chemical and physical properties to an organic compound. Different functional groups give us totally different real-world traits. For example, carboxylic acids and esters contain functional groups that create the delicious fragrances of fruits and serve as the building blocks for fats and oils. Meanwhile, the functional group in aldehydes gives them incredibly pungent odors. It's all about the group. Section 2. Alcohols. Hydroxyls in action. You know, when most people hear the word alcohol, they immediately think of two things: large-scale ethanol production for beverages and fuel, or the clinical rubbing alcohol used in hospitals. But chemically speaking, the alcohol family is incredibly diverse. An alcohol is essentially a derivative of a basic hydrocarbon. You create an alcohol by taking an alkane, like methane or ethene, and replacing one or more of its hydrogen atoms with a hydroxyl group, which is just an oxygen bonded to a hydrogen, written as OH. The absolutely crucial part here is that this hydroxyl group is directly attached to a carbon atom of an aliphatic system. Swap out a hydrogen for a hydroxyl group, and boom, you've got methanol and ethanol. Section 3. Classifying and naming alcohols. Because organic chemistry is a highly structured discipline, we don't just lump all alcohols together. We classify them methodically based on the exact number of hydroxyl groups they contain in their molecular structure. So, if an alcohol has just one hydroxyl group, it's monohydric. Simple enough. But if it features exactly two hydroxyl groups, like ethane 1,2-diol, commonly known as ethylene glycol, well, then it's a dihydric alcohol, also known as a glycol or a diol. Let's move to and see how this builds. If we add a third hydroxyl group, we step up to a trihydric alcohol. A perfect example of this is propane 1,2,3-triol, which you probably know much better as glycerine or glycerol. Notice the three separate OH groups attached to that three-carbon backbone. And as a quick rule, any alcohol with three or more hydroxyl groups falls into the broader category of polyhydric alcohols. Zooming back in on monohydric alcohols, the ones with just one OH group, they actually get a special subclassification based on the specific carbon atom the hydroxyl group is attached to. We call them primary, secondary, or tertiary. In a tertiary alcohol, like the examples of 2-methyl-2-propanol and 2-methyl-2-butanol, the carbon holding the hydroxyl group is itself completely surrounded, attached directly to three other alkyl groups. To keep all these wild structures straight, chemists use IUPAC naming rules. It's actually a very logical system. First, you find the longest carbon chain and drop the E from the alkane name, replacing it with -ol. So methane becomes methanol. Makes sense, right? Then you number the chains starting from the end nearest to the OH group and use those numbers to say exactly where the hydroxyl and any other branches live. And if you have a polyhydric alcohol with multiple hydroxyls, you keep the E and just add a prefix, giving you names like diol or triol. Section 4. Ethers, the oxygen bridge. Unlike some of their more reactive cousins, ethers are relatively resistant to chemical transformations. Because of this rugged stability, they are incredibly valuable in the lab.
frequently acting as the crucial neutral solvents needed for other chemical reactions to even take place. The structure of an ether is beautiful in its simplicity. Instead of the oxygen hanging off the end of a molecule with a hydrogen attached, the oxygen atom drops right into the middle of the chain, acting as a literal bridge connecting two separate alkyl groups. Their common names are just as simple. You literally just read the names of the two alkyl groups connected to the oxygen in alphabetical order and tack the word ether onto the end. For instance, ethyl, then methyl, ether.
Now, what's really interesting about this is how the official IUCAP system handles ethers. Instead of viewing them as two groups bridged by oxygen, IUPAC names them as a main alkane chain that just happens to have an oxygen-based attachment known as an alkoxy substituent. You drop the YL from the shorter alkyl group and replace it with oxy, so a methyl group bonded to the oxygen becomes methoxy, sitting on a parent butane chain. It's just a slightly different way of looking at the exact same bridge.
Section 5. Aldehydes, ketones, and carbonyls.
This next chemical neighborhood is heavily found in nature and boasts some of the most distinct smells in all of organic chemistry. But before we meet the molecules, we've got to understand their anchor. A carbonyl group is a functional group consisting of a carbon atom connected by a double bond directly to an oxygen atom. That double bond, C double bond O, is the defining feature here, and it is the rock-solid foundation for both aldehydes and ketones. So how do we tell an aldehyde from a ketone if they both have this double-bonded carbonyl group? Here is your straightforward rule of thumb. It all depends on what else is attached to that carbon. In an aldehyde, the carbonyl carbon is bonded to at least one hydrogen atom, putting it right at the end of a chain. In a ketone, that carbonyl carbon is sandwiched in the middle, bonded to two other carbon atoms. Hydrogen means aldehyde, carbons mean ketone. Simple as that. I want to pause for a second and throw this over to you. Based on the rules we just established about what makes an aldehyde and what makes a ketone, what do you think the absolutely simplest version of each would look like? Like, how few carbons can we get away with while still following the rules?
Well, here's the answer for the aldehydes. Because an aldehyde only requires the carbonyl group to be bonded to at least one hydrogen, the simplest possible aldehyde just uses another hydrogen for its second bond. This is methanol, historically known as formaldehyde. Add a methyl group, and you get ethanol, then propanol. Notice the IUPAC naming convention here. We change the parent alkane suffix to -al to indicate the aldehyde functional group.
Section 6. Polarity and physical properties. Drawing structures on paper is great, but we really need to know how these functional groups rewrite physical behavior out in the real world. Why are some liquids? Why do some boil so easily? It all comes back to the oxygen atom. Oxygen is highly electronegative. It aggressively pulls electrons toward itself, creating polarity. And this brilliantly illustrates how, in alcohols, this creates a partial negative charge on the oxygen and a partial positive charge on the hydrogen. These opposite charges attract each other across different molecules, creating a super strong network of what we call hydrogen bonding. This strong intermolecular grip is the exact reason why even small, low molecular weight alcohols are liquids at room temperature rather than gases. We see a very similar story play out with our carbonyl groups in aldehydes and ketones. The carbon-oxygen double bond is polar, oxygen hoards the electrons, becoming partially negative, while the carbon is left partially positive. Because of this polarity, aldehydes and ketones interact through dipole-dipole interactions. Furthermore, they can actually interact with water molecules through hydrogen bonding, making the smaller aldehydes and ketones highly soluble in water. So, the crucial point is, we can see the impact of all this just by comparing boiling points. Look at butanone and butanol, a ketone and an aldehyde. They have a molecular mass of 72. Now look at pentane, a basic non-polar hydrocarbon, which also has a mass of 72. You would think similar mass means similar physical traits, right? Wrong. Pentane boils at a relatively low 36 degrees Celsius. But because of the polarity from the carbonyl groups, butanone boils at 76 degrees, and butanol at a whopping 80 degrees. Polarity creates a stickiness between molecules that requires way more heat energy to break apart.
And that brings us to the end of our explainer. It really is breathtaking when you think about it. By simply adding a single oxygen atom in different arrangements, a hydroxyl group here, an oxygen bridge there, or a double-bonded carbonyl, we completely rewrite the rules of chemistry. We literally turn gases into liquids, create intense fruit fragrances, and generate absolutely crucial biological and industrial solvents. One tiny elemental modification changes the world.
So I leave you with this. The next time you smell a sweet fruit or use rubbing alcohol, how will you look at everyday molecules differently? Thanks for learning with me today, and I'll catch you on the next explainer.